Today, this is part 2 of our webinar series on porosity. And today, what we're going to be talking about is controlling porosity through process parameters. So before I get into the webinar, let me introduce myself again briefly. My name is Steve Midson. I'm president of the Midson Group, a Denver-based consulting company, basically specializing in casting and materials. I got a PhD in metallurgy from the University of Sheffield in England, and around 30 years or so casting and metallurgical experience. I served as Chief Operating Officer of 2 commercial casting companies, Director of a development and prototyping company, and then I started my career working in the R&D labs for 2 different Fortune 500 companies. I'm also an adjunct professor, a part-time professor at the Colorado School of Mines here in Colorado. I teach the foundry metallurgy to undergraduates. Quite active in NADCA. I'm chair of the NADCA Dye Materials Committee and a member of the NADCA R&D Committee. And I've authored probably more than 50 technical papers, mostly in the area of casting. So that's kind of a little bit about me. Let's get into the webinar. Okay, so let's start with a little bit of background. It's been a week since we had the last seminar, the part 1. We'll have, I understand we've got a few new people online, so let's give a little bit of background in terms of how we got to this point. What we're going to do is discuss parameters that affect porosity. Some of these are well known, very well researched, and some are not quite as well understood. We'll have a discussion of factors that affect porosity. Some of these are well known: intensification, spray, dye design, alloy, degassing, things like that. As we go through, I'm going to give some examples of technical papers that have been published over the years, and many of these you can download from NADCA. If you're an individual member or corporate member, you can go online and get those for free, and it's well worth actually going and looking at the original data. So what we're going to talk about is basically how we can use this data to improve the quality of our die castings. In the first webinar, we talked about this survey, introduced this survey. It's kind of shown here, this pie chart in the bottom right here, where NADCA had done a survey of end users of die castings and asked them basically what the biggest problems they had with die castings are. And as you can see here, the biggest was porosity. 35% or so of the end users said that porosity was their biggest problem, while another 32% said that other defects were their biggest problems. And often these defects originate from similar issues that cause porosity. So basically 2/3 of the respondents, 35% and 32%, 67%, said that their problems with die casting either came from porosity or from similar causes as porosity. So basically what we're saying is if we can control the porosity formation in die castings, we can have control over many of the types of problems that these end users have with die castings. We know many of the process parameters that control porosity. We just talked about a few of them in terms of intensification, fill time, die temperature, metal temperature, things like that. And we have to be careful. This implies that we have this great need for great control over the process. Certainly there's lots of buttons on both the die casting machine and the peripheral equipment. And Alex Monroe at NADCA used to refer to this as just play with the knob syndrome. So just turn the timer to the correct setting on the ladle, the shot delay, or some other kind of piece of equipment, and that should allow me to fix my problems. Well, you know, that's really shooting in the dark. That's really not a good approach in terms of trying to fix your porosity problems. What we do is we need to have a physical understanding of the effect that each parameter has on the formation of the porosity. So in the first webinar, we talked about how porosity is a characteristic of the die casting process. Basically, we should expect it to be there. So we need a physics-based approach in terms of controlling porosity, in terms of controlling where it is, the distribution, the size, and things like that. This could involve design of experiments. That could be an important part of it in your facility, in your plant. So if we keep on going in terms of some background, again, we talked about this in detail in webinar number 1, where there's basically 2 sources of porosity in die castings. We have solidification shrinkage, the volumetric contraction that occurs as we go from liquid to solid, and then there's gas entrapment from various sources. In terms of the volumetric shrinkage, again, we talked about this in terms of aluminum alloys. It's around a 6% volumetric contraction upon solidification. With zinc, it's a little bit less, 3.5 to 4% or so. And then magnesium somewhere in the middle, probably about 4.5% or so. But if you go and look at the literature, when people talk about the level of porosity in die castings, it's very rare to see a casting that's got more than 3% porosity. So this implies that we can't discount one source of porosity over the other. We're going to get both air entrapment and shrinkage porosity in the die castings. And so we also discussed these 2 types of porosity in a little bit more detail. The picture here on the left, we have these smooth pores, and the picture on the right, we have these rough, jagged pores. And we talked a little bit about the physics of the pore formation. The smooth pores tend to be associated with higher liquid fraction. They tend to form early in the solidification process when it's mostly liquid around, so there's still a high liquid fraction. Often this is associated with entrapped gas, but not always. And then the jagged pores, the ones on the right, tend to form at lower liquid fractions. And so again, we talked a little bit about this. On the top left here, we've got a kind of a schematic a model of a casting. If we split it up and cut it and polish it, we can see the mostly spherical pores here. And so the question is, what's the source of this porosity? It's smooth, so it must be gas porosity, right? Well, no. The answer, as we talked about last week, is it depends. In the bottom right, we have this drawing that we talked about in detail last week. And what this is looking at is a paper from the 1994 American Foundry Society transactions, when it's talking about the effect of hydrogen concentration on the shape of the pore that will form during solidification. So in this case, all these pores are forming from gas, from dissolved hydrogen. But if you look at the first column here, this is very high hydrogen concentration. The pores are forming very early in the solidification process. We only have a very few grains forming, and therefore the pores are spherical. As we move to the right, we're talking about lower hydrogen concentrations, and therefore the pores are forming later in the solidification process, and they become more jagged in column 2, very jagged in column 3, and basically just we have the final solidification here. And so porosity is going from smooth to jagged based on the hydrogen concentration, based on when it forms during the solidification process. Early in the solidification process, they're spherical. Late, they're jagged. But these are all coming from gas. So what we want to talk about today then basically is process parameters that can affect porosity. So let's take a little bit of a look in terms of what simulation can tell us. This is data generated from Alex Monroe, and basically what we're looking at is the effect that different process parameters have on porosity. At the top, these are having the largest effect on porosity, and at the bottom here, these are having the smallest effect on porosity. And so at the top, we've got intensification pressure, and both the literature, simulation, and also our own experience tells us that intensification has by far and away the largest impact on shrinkage porosity. Unfortunately, what we find, though, is above 150 bar or so, 2,500 psi, we find that intensification pressure has a diminishing return. What we mean by this is, for instance, if we don't intensify, if we have a zero pressure intensification, we're going to get about 6% porosity, because that's the volumetric contraction that we get upon solidifying aluminum. If we apply 2,500 psi, maybe we can shrink that down to 1% porosity or so. Above this, we get a diminishing effect. If we go above 2,500 psi to maybe 5,000 psi, the porosity is only slightly reduced. Maybe we go from 1% to 0.75% or so. So we get this diminishing effect with pressure, and we'll talk about this later as we go through today's webinar. Second here, we're talking about spray. So what we're saying is that spray can have the second largest effect, and with spray we can locally control the dye temperature, we can create cold spots on the dye, we can change the distribution of the dye, and we can control, therefore, where the porosity ends up. Hot areas of the dye tend to attract porosity, colder spots tend to push porosity away. That doesn't mean that you should just make your whole dye cold. As we'll talk about that, ideally what we really would like to have is directional acidification from the extremities of the casting back towards the gate, although that's often difficult to control. And when we talk about this later on in today's webinar, we'll talk about that in a bit more detail. Then in the first webinar, we also talked about the third item here, the mushy zone permeability, or the effect of alloy type on solidification and porosity distribution. In terms of the shorter freezing range alloys and the wider freezing range alloys, these is going to affect the size and distribution of the porosity. And then basically the next three items, the in-gate height, initial metal temperature, dwell time, these tend to have a smaller effect on porosity. The effects are still real. It may be able to help you in terms of minimizing your porosity, but the effects are generally not as strong as the previous three parameters we just talked about, intensification, spray, and mushy zone permeability. In terms of processing parameters, there are a number of processing parameters obviously we can look at. We've got shot profile in terms of the fast shot, the slow shot, and the pre-fill. Note that velocities matter both in hot chamber, not just in cold chamber, and we'll talk about why that is later on in the presentation. We'll also talk a little bit about thermal lines. We've got a little model here on the top where this is actually for a squeeze casting simulation, and the thermal lines are shown. The thermal lines are going basically directly through the cavity inserts, and we'll talk about exactly how much control we have over dye temperature. And then spray, both in terms of spray time and flow rate. And we'll see that spray doesn't give us much control over dye temperature as we would like, and maybe not as much control over dye temperature as we think we have. We'll talk about venting and vacuum a little bit today, but we'll talk about more about that in the next webinar in part 3. Obviously, if we're using vents or vacuum, we need to make sure that either of them are working correctly. If the vents are blocked, obviously that's not going to work. We're not going to get air going out of the cavity. We're going to trap it in the cavity and get more porosity than we expect. Then in terms of melt cleanliness, we'll talk a little bit about that. And then alloy composition. We had talked a little bit about this in the first webinar, where we talked about the effect of alloy composition on porosity formation in terms of the size and distribution. We talked about the effect of the width of this mushy zone. So on the left here we've got the solid. On the right here we've got the liquid. We have this mushy zone, which is partially solid, partially liquid. To be successful, we've got to feed the liquid past these dendrites to get down to the base here, which is where the solidification shrinkage is really going to be forming. And so for narrow freezing range alloys, we tend to get larger pores, which are generally easier to detect on X-ray. With a wider freezing range alloy, we get smaller, better distributed pores. Still there, we're still getting the same amount of porosity, but it can be more difficult to detect on X-ray. But alternatively, it could create more of a problem if you've got a pressure type part. So those are some of the things you've got to think about, and we'll talk about that a little bit later on in today's webinar. So how do we start to evaluate these process parameters? So again, we should really think of porosity as a superimposed problems, coming both from shrinkage as well as coming from gas entrapment. So typically in die casting, shrinkage is going to dominate the location of the porosity, and then gas entrapment is going to either increase or decrease the amount of that porosity. And then the entrapped gas often becomes associated with shrinkage. And again, this is another one of the reasons why often we can see shrinkage pores that seem to have spherical shape as opposed to the jagged shape we would expect. So if we look at this graph, what we're looking at here is a simulation. On the left, we're looking at the pressure, and then we've got the simulation time. And the right axis shows the amount of porosity that's forming. And so if we look at, as the simulation runs on, the gate starts to freeze, and so the pressure in the cavity starts to drop. We start to solidify the casting, and so we start to form the shrinkage porosity. And so this black dotted line is showing how much shrinkage porosity we're getting in the casting just from shrinkage alone. So you can see we're getting somewhere between 1.5% and 2% or so from shrinkage. The red line, however, shows what happens when we add in the gas entrapment, when we superimpose a gas entrapment. And so with the gas, we're basically adding another 0.5% porosity or so, at least for this simulation. So we're increasing the total amount of porosity from somewhere around 1.75% to about 2.25%. So that kind of shows a little bit about the superimposition of shrinkage and gas entrapment. So let's talk a little bit about the impact of changing the process parameters and the impact this can have on the porosity levels and distribution. And let's start with a discussion of pressure. So this is a great paper from the 2001 NADCA Transactions paper 073, and these guys performed some experimental work. And what they did is define an inverse relationship between the intensification, pressure, and porosity, i.e., as the pressure increases, the amount of porosity decreases. And so, again, no great surprise there. These guys, however, what they did is they defined the equation shown here where the percentage porosity is a constant divided by the intensification pressure plus a second constant. And what NADCA's done is got some data from some other technical papers, determined the values for A and B, and came up with the graph shown here on the upper right. And what it shows is kind of what we were talking about earlier, is that the pressure, the porosity content initially decreases with an increase in pressure. But once you get to, I don't know, maybe 3,000 psi or so, we don't see a tremendous additional drop in porosity content as we go to higher pressures. We have some effect, but not as big as initially. The lower graph here shows some real data. This is looking at actually the density of die castings, i.e., we increase the density as we get a decrease in porosity because we're getting rid of the holes, and so we see a slight increase in density with increase in pressure. One thing we do need to keep in mind, however, is that when we apply pressure to any liquid, whether it's a liquid aluminum or in a hydraulic system or just water, the pressure in the liquid is the same at any point in that liquid. What this means is that, therefore, we can't move the porosity around from pressure alone. We can reduce the size of the pore, we'll talk about that in a few minutes, but we can't move it around. So if we have a pore that's close to a critical area, we can't move it away from that critical area from pressure alone. We talked a little bit about this, but we can reduce the size of it, and this is what we talked about in the first webinar, where Boyle's law shows the impact of pressure will have upon the volume. So the volume depends upon the initial pressure divided by the intensification pressure. So we can reduce the size from pressure, but we can't change the location from pressure. So let's talk a little bit about some of the shot parameters in the shot end. We've talked a little bit about pressure, but there are other parameters that we can play with. This is really more to do with cold chamber. We'll talk a little bit about hot chamber later. But in terms of parameters, we have pore height, pore time, we've got wait time. But the ones shown in red are really the more important ones in terms of percent fill, the slow shot velocity, the fast shot velocity, the switchover point, i.e. in terms of the amount of pre-fill. And People have looked at these parameters for a long time. Probably the most famous is Garber's work from the 1980s, but it goes back even further than that, back to the 1960s or so. As a starting point, let's talk about fill time. Fill time is basically how we control our entire process. And the NADCA calculation for fill time, which is shown here, is actually based on real science. It actually comes from a paper from 1968 and certainly is worth reading if you've got the time. But it's a good place to start in terms of our examination of porosity. So why does fill time matter? So basically this is a basis for the estimation of all of the parameters, when we're designing a die casting in terms of the gate area, the gate velocity, basically provides control over the entire process. So if we get the fill time wrong, that essentially pushes us into an area where it's very difficult to control porosity, so we need to get that right. Fill time is basically how we control our entire process. And the NADCA calculation for fill time, which is shown here, is actually based on real science. It actually comes from a paper from 1968 and certainly is worth reading if you've got the time. But it's a good place to start in terms of our examination of porosity. So why does fill time matter? So basically this is a basis for the estimation of all of the parameters, when we're designing a die casting in terms of the gate area, the gate velocity, basically provides control over the entire process. So if we get the fill time wrong, that essentially pushes us into an area where it's very difficult to control porosity, so we need to get that right. And here's another thought about fill time. This is more recent work that was actually presented at the last year's Congress, 2012 in Indianapolis. Basically, it's addressing the fact that we have a problem that we don't really know the temperature that we're filling our die with. Here we're looking at the entire process of getting the metal from the furnace on the left all the way into the die, so through the ladle, through pouring, through into the shot sleeve, and then actually filling the die. And the actual die filling time, as we can see here, is a very small percentage of the entire process, maybe as little as 1% of a much longer process. So if we want to control the entire process, we have to look at how the metal gets into the shot sleeve, not just how fast we're filling the die. So if we look in a bit more detail at the actual shot profile, this is obviously a traditional shot profile. So the die filling time is essentially the fast part, the second stage, is shown here of the shot profile. So the time to fill the cavity is basically the time from the start of the fast shot to the end of the profile. Obviously the slow shot is, the slow shot velocity is also very important, certainly in cold chamber where we're controlling the wave formation in the shot sleeve, because we need to minimize the amount of air trapped as we fill the sleeve. So let's talk a little bit about the slow shot velocity, the first stage speed. This is some graph. Again, this is from 1997 transactions, the paper numbers identified here. And what it's showing is the effect of the slow shot velocity upon the relative porosity. And we can clearly see that if we want to reduce porosity, we need to use a slower first stage velocity. So a general rule of thumb is the slower the better with the slow shot velocity. Obviously we can't go too slow. We don't want to get too much solidification in the shot sleeve. But in general, the slower the better for the first stage velocity, for the slow shot velocity. So it kind of raises a question in terms of, how slow can we go? If I go slowly in the shot sleeve, it's taking more time. So really I want to go faster. If I go faster, am I going to cause myself a problem with porosities we just talked about on the previous slide? So this is basically the thinking that prompted the work of Gerber back in the 1980s. This is where his equation shown here on the right-hand side comes from. And the idea was to basically calculate the maximum speed I can move the plunger at during the slow shot velocity. It's obviously based on the plunger diameter and the fill ratio. Bear in mind, as shown here in the middle of the slide here, that Gerber's calculation for the slow shot velocity basically only works for a fill ratio bigger than 50% or so. And so there's been some more recent work than Gerber's, For instance, Marilyn Thome at the Ohio State University, she came up with a better model in the 1990s. What she said is that we should use an accelerating slow shot velocity. So instead of using a constant velocity, as Gerber pointed out, she said it should be an accelerating slow shot velocity. But obviously, if you're going to do that, you have to have a die casting machine with good control over plunger velocity to allow you to program an accelerating plunger velocity. But work's still going on in this area. So even as recently as 2009, a new model was proposed. So let's talk a little bit about Marilyn Thome's model. And these two diagrams show the idea behind the accelerating profiles. The upper diagram shows the normal idea of a constant plunger velocity. It tends to create just one wave. So we can see the wave forming here and the normal level in the plunger here. And this tends to be a bit more difficult to control. And certainly it's going to result in gas entrapment. If this rather severe wave that we produce here, if this wave breaks, we're going to get gas entrapment here in the sleeve. It's going to get injected with our metal into the casting, and it's going to cause porosity. So the lower diagram shows Thome's concept, and what she said is that we should use this accelerating slow shot velocity. So instead of producing one single wave, we're creating a series of smaller waves. It becomes easy to control. As you can see here, the severity of the wave is much less. It's much less likely to break, and this is especially true for the low fill ratios, fill percent in the sleeve. And then here's some additional information about accelerating slow shot velocities. This is actually work performed prior to Marilyn Thome. This is from the 1991 transactions. Again, the paper numbers defined here. And again, it looked at accelerating slow shot profiles, accelerating at a constant rate. And so what we have is we've got 4 graphs here, where each of the graphs is showing the plunger velocity on the y-axis, plunger position on the x-axis. It's all for 4-inch diameter sleeves, but it's for different fill ratios. So 20% fill, 30% fill, 50% fill, and 70% fill. And so it's looking at different acceleration rates under these conditions. And the results are summarized up here in the top left, where we're showing the amount of the entrapped air volume for the different acceleration rates in inches per second per inch, and then also for the different fill ratios. And so what we can see is down here, the amount of entrapped air is low. So basically for an acceleration rate of below 4 inches per second per inch or so, and then above that rate, the amount of entrapped air becomes significantly higher. So again, this is giving you additional information in terms of the optimum slow shot velocity to be used in cold chamber die casting. Fast shot velocity, and again, here's some data again from the 1997 transactions, the paper numbers given here. And now we're looking at the impact of fast shot velocity on porosity. This is really independent of whether we're talking about cold chamber or hot chamber. And in some ways, maybe this these data are a little bit confusing, because it's certainly different than what we've heard from NADCA for years. What it's showing, or what it seems to show, is that the lower the fast shot velocity, the lower the porosity. It's quite significant. You go from 0.8% porosity up here at high speeds to 0.4 to 0.6 at the lower speeds. So when you initially think about this, it doesn't make sense, because normally what we say is faster is better. But if we look a little bit more closely at the data, maybe we can make a little bit more sense out of it. If we look at this low speed area, basically we've got these open triangles, and if we look at the legend here, the open triangles, we fail both X-ray and surface inspection, but it has a lower overall porosity. So what's going on? So probably what's happening here at low speed, instead of distributing the porosity uniformly, we're getting, instead of getting lots of small pores, we're getting a few large pores. And so it's these large pores that's going to cause us to fail X-ray. As we go faster, now we get to the area here where we get the black diamonds. This kind of seems to be a bit of a sweet spot. So here we've passed both X-ray and passed surface inspection. So although the overall porosity was higher, we seem to be getting a better distribution of porosity, a smaller porosity that allows us to pass X-ray. If we go even faster, now we get to these white squares up here. And so if we look at the legend for the white squares, we failed X-ray but passed surface inspection. So maybe what's happening is that we're injecting the metal so fast that maybe we're blocking the vents very early in the casting process, allowing us to trap more gas, fail X-ray, but again, by going at high speed, we're getting a good surface finish in our casting. So let's move on. Let's talk a little bit about pouring into the sleeve. Certainly, when we dump liquid metal into the sleeve, it's going to move around. Is this going to affect the formation of the wave during the slow shot velocity? Well, we'll talk a little bit about that in the next few slides. But certainly pouring closer to the pore hole is better because we're basically minimizing the height over which we're pouring at. And also pouring smoothly helps us as well. We shouldn't stop and start. That can create broken flow, can create oxides, and problems with our castings in that way. So let's talk a little bit about pouring in terms of the delay time. And what we're looking at here again is experimental data. Up here we're looking at percentage fill from 25, 50, 75%. Across the top we're looking at shot delay time, 0 delay, 0.7 seconds delay, 1.5 seconds delay. And then we've got pouring rate, low, medium, high for each one of these, low, medium, high. And then we've got a starting position. So we've got a lot of data shown here in this graph. What we're showing here from the legend is that the shaded areas are basically high porosity, more than 1 cubic inch of air entrapped. The unshaded areas are really where we want to be in terms of lower amounts of trapped air. And what it's showing to me is basically, at least for the low percentage fills, 25, 50, as we have an increased delay time, we're actually increasing the amount of entrapped air. And so what it's suggesting here is that waiting for the turbulence from the pore to go away is actually hurting us instead. It's not helping us. So why should longer wait times hurt? As I say, you kind of think intuitively longer wait times would help. As it's kind of, it's helping to reduce that turbulence from the pouring. So here again, we've got data. This is from the transactions from all the way back to '68. What they did is they used thermocouples to measure the temperature of the metal in the sleeve, in the shot sleeve. So we're looking end on in the shot sleeve here, looking from the side, and you can see they've got 5 or 6 thermocouples coming in, and they actually measured the temperature as the metal sat in the shot sleeve. And so this graph, what we're looking at here is actually the temperature against time for the 6 different thermocouples that I showed in the previous graph. And what it shows is that after a pretty short period of time, around 2 seconds or so for their work, for their experimental conditions, we start to get this dramatic loss of temperature in the shot sleeve. So if we wait too long, and too long is not a very long time, we get in lots of pre-solidification in the sleeve. That's maybe causing us problems. Maybe we have to go faster to prevent the non-fills. We talked a little bit about this earlier. In terms of going very fast can produce problems. So the bottom line, basically what these data are showing is that the longer wait times are bad, and then we're going to increase the amount of porosity in our castings. So one other thing, talking about shot end pour time, this is unique to a hot chamber, is that we can have a problem occurring when we're returning the piston back to its home position and basically refilling the gooseneck with metal. What we need to do is ensure that we don't entrap air at the tip of the piston. Obviously this is bad as we're going to inject that air into the cavity, or we could inject that air into the cavity and cause porosity. If we do have this problem, if we do entrap air here at the tip, we get this characteristic or up and down in the pressure in the shot cylinder. So we need to watch out for this. If we see this kind of characteristic behavior. This is very characteristic of entrapping air down here in the at the tip during fill-in of the gooseneck. Let's talk a little bit about pre-fill. Pre-fill is quite commonly used to help control porosity in die castings. Again, NADCA did a survey and found that around 50% or so of die casters have used pre-fill from time to time in filling their castings. Traditionally we would start the fast velocity either when the metal's at the gate or just before the gate. But with pre-fill, what happens is that we basically continue the slow shot velocity into the cavity, and it's certainly been shown that it can reduce porosity in die castings. Normally pre-fill is kept below 45% or so, and the graph at the bottom right here kind of presents some data. Again, this is from a 1997 transactions paper. So as we delay the onset of the fast velocity, so basically the second stage start is going from 300 to 400 to 500 to 600 millimeters. What it shows is that, at least for the conditions examined in this study, we were able to reduce the amount of porosity in the castings. And certainly a number of papers have shown this. We get similar results based on percent of castings passing or failing X-rays. Pre-fill, so pre-fill can be beneficial. Basically, the longer delay of the fast shot, the lower the porosity. However, it does depend upon the geometry of the casting, and that's kind of shown here in this series of graphs. So this is again good data from a 1999 paper from the transactions, the effect of pre-fill. And what they did is they looked at two different die cavities, or they modified their die cavity. So here we have a simple plate where we're gating it here with vents on the end, and then what they did is they put baffles in the die to basically have a more tortuous path in terms of actually filling the part. And so they looked at the effect of pre-fill for the two different dies based on different slow shot velocities. And so for the simple plate die, the data is shown here on the bottom left, where again we're looking at air entrapment against percentage of cavity pre-fill for two different slow shot velocities. And we can see generally we get a decrease in the amount of porosity until we get to 30%. For the lower slow shot velocity, it stays pretty low, but for the high slow shot velocity, we get an increase in gas entrapment if we go to 40% pre-fill. However, if we look at the more complicated die, the data shown here on the bottom right, again, air entrapment versus percentage pre-fill. In this case, the amount of porosity is higher, not surprising because it's a more complex, more turbulent fill. But for all conditions, we get a decrease in the amount of porosity as we increase the amount of pre-fill. Let's talk a little bit about vents and vacuum. Obviously, both can help remove air from the cavity in terms of reducing porosity. However, we obviously got to make sure that both are working well. Vents must be open. We'll talk about that a little bit later. And certainly, one of the things worth talking about is this new high vacuum process. This is where you get vacuum, very low levels of vacuum, 100 millibars, maybe even 50 millibars, which is actually quite challenging to get in a die casting die. So some of these new high vacuum systems, such as a high Q process, a Bacurau process, enable you to get very low levels of vacuum, but you have to have a specially designed die to do that. Let's talk a little bit about alloy and melt cleanliness. We talked about hydrogen degassing and hydrogen concentrations in the first webinar, so I don't think we need to go over that in much detail. One other point that's worth mentioning is that certainly dirty metal, in terms of lots of inclusions or foreign material, that can also cause problems in terms of increased gas porosity. It's similar to kind of seeding of clouds, where they seed the cloud to try and get it to rain. The seeding creates water particles that turn into rain. In our case, our foreign particles will seed the porosity and cause porosity to come out. So oxides, inclusions, foreign materials can cause increases in porosity in our castings. And then again, talking about alloys, we talked about this a little bit in the last webinar, but this is actually data taken from a Congress paper from 1987. What they did is they modified the silicon content of the alloy. So they looked at alloy 380, which has a nominal 8.5% silicon, and they looked at alloy 383, which has a nominal 10.5% silicon. And what they found is they could not get a good casting with the 383. They couldn't get one that would pass X-ray inspection, but when they changed over to alloy 380, it was not a problem passing X-ray inspection. And so this can be explained, again, talking about the width of the freezing zone, the width of the mushy zone we talked about previously. If you look at the aluminum silicon phase diagram in the bottom right here, this is the freezing range for the 383 alloy. It's pretty narrow, while the freezing range for the 380 alloy is much wider. And so we talked about this in the first webinar. Short freezing range alloys such as 383 tend to produce macro porosity, while wider freezing range alloys such as 380 tend to produce wider dispersed micro porosity, smaller porosity. So we're talking about in both alloys we're going to get about the same amount of porosity, but we get smaller and wider distributed porosity in the 380. It's kind of shown here on the top right. And so this can allow us to pass X-ray inspection if we're having problems with a large pore maybe in 383. The iron concentration of the alloy can also affect things. If you have a high iron concentration, during solidification, you tend to get aluminum iron platelets coming out in the microstructure. These platelets form pretty early and can block the feeding channels that we've talked about in terms of how we actually feed the shrinkage. And so high iron can also give you high levels of porosity in your castings. So let's talk a little bit about die temperature. This is really the last category that can have a big impact upon reducing porosity. The goal here is to get directional solidification, as we talked about. If we can get directional solidification from the extremity of the casting back towards the gate, that helps us feed the shrinkage, because the additional metal we're feeding with is coming through the gate. And so avoiding isolated heavy sections in the casting is a good thing. So over the next few slides or so, we're going to talk about thermal control in the die, the effect of the thermal control from internal cooling, effective thermal control from spray, in terms of how those can actually affect our porosity and what effect, how much control we really have over each of these two processes. So we really need to understand our heat removal rate, HRR, heat removal rate, basically from the thermal lines. Either we're going to have oil lines or water lines. We can certainly use computer control these days. Units are available that allow us to kind of turn on and off or turn up and down the flow of the oil or the water based on temperature requirements. And we also need to understand then the heat removal rates from the spray. So this is data that I showed in the first webinar, looking at the effect of spray on heat removal. As we talked about, really the amount of heat removal is not intuitive in terms of how it works. It doesn't necessarily act as we think. We can't just keep on increasing the amount of spray and expect to keep on getting additional cooling of the die. So this is experimental work in terms of the amount of heat flux, i.e. the amount of heat extracted with time for different spray rates from 0.1 gallons per minute to 0.5 gallons per minute. So if we go from 0.1 to 0.2, which is a solid curve, up to one of these dotted curves, we get a slight increase in heat extraction rate. I should say this is obviously with the experimental conditions used here. The flow rates in your die might be different. But as in the test done here, as we go from 0.2 to 0.5, we essentially get no more heat extraction. It's not helping. We're just basically wasting our time. In fact, we might actually be hurting ourselves, because if we have a higher flow rate, we're getting more lube on the die, as we talked about last week. That can cause more porosity. We got more water around, and again, we might get, if we don't get rid of all the water, we may get vaporization and porosity in that way. So it's reasonably limited in terms of what we can do with spray. We don't have total control over controlling the dye with spray. So this here, we're talking about the BO number. We're not going to go into all this information here, but this is interesting information if you want to look it up later. Let's focus on the diagram here on the right. So if the BO number is very, very small, much less than 1, then we basically get this temperature profile shown here. If the BO number is very large, down here, then we get more of a gradient through our dye material. So for a 1-inch thickness of H13, basically the BO number is 4, which is obviously much greater than 1, and so we get this kind of data shown here. For the, if we think about a much higher thermal conductivity material such as amberloy, which people use in parts of their dye, the BO number is 0.2 for a 1-inch thickness of amberloy, so that's much less than 1, and so we get this kind of gradient with amberloy. So what does this mean in terms of heat extraction? What it means is that we're looking at here is the temperature of the dye versus time for different depths into the dye. So 1.5 millimeters are basically adjacent to the surface versus 35 millimeters. 35 millimeters is just less than an inch and a half. So if we make our casting or spray our dye at the surface, 1.5 millimeters, we see a big impact. But 35 millimeters into the dye, basically we see no change at all. So there's no change in the dye temperature throughout the die casting cycle at only an inch and a half into the dye. So we have this kind of transient layer. We have where we can affect the surface, but only an inch and a half into the dye, we have very limited effect in terms of changing it, either by dye spray or by the cooling lines within the 60 seconds or so of a die casting cycle. So we have this transient layer. It's a big deal for us die castings because it limits our ability to control the dye temperature and therefore to control porosity. And we can affect the surface, but we have very limited effect below the transient layer of about 1.5 inches or so. And this is one of the reasons why spray doesn't really work the more we apply. We can calculate this transient layer. This is the math shown here. Again, I'm not going to go into detail on the math, but we can use this math to kind of make predictions in terms of both the transient response to heating, which is shown on this graph, and we can look at the transient responses to spray, which we'll see on the next graph. And so this is basically looking at distance from the surface versus temperature with time. And so basically 10 seconds into the cycle or so, the triangle shown here, we've only transferred the heat about 4 centimeters into the dye. Again, this is just a little bit more than an inch and a half below the dye surface. So obviously we're getting a very slow response in terms of getting heat into the dye. And we also have a similar slow response in terms of getting heat out of the dye. So this is the inverse of what we just talked about. Now we've got the dye at room temperature. We're basically spraying room temperature water onto the dye. Again, we're looking at temperature change versus distance from the surface. And again, the dye is very slow to respond in terms of actually cooling the interior of the dye. And so this is why we can have limited effect in terms of what we're doing in terms of spraying. So we can do our transient layer calculations. This actually shows how to do it, where the depth is to do with the cycle time and the thermal diffusivity. Thermal diffusivity is defined here in terms of thermal conductivity, the density, and the heat capacity. And for H13 steels, basically you use these equations here for in terms of meters or in inches, depending upon how you want to do the calculation. So you can calculate your transient layer in the die. And again, this is basically showing the data we talked about before, where we're looking at the heat transfer against time, and at low flow rates from 0.1 to 0.2, yes, we can change it, but from 0.2 upwards to 0.5 basically has no effect on the heat transfer rate in the die. So what does this mean? What this means is that as H13, as we know, is a relatively poor conductor of heat. And so within the average die casting cycle, 60 seconds or so, the transient temperature depth is about 1 inch or so. So thermal controls may not be as effective as we'd like, or maybe as we think. So for example, for a 3/8 inch diameter water line, if we double the flow rate from 2 to 4 gallons a minute, all we're doing is getting a 5% increase in the heat removal. So changing the water flow rate had only a very minimal effect in terms of the heat removal rate. And certainly, as we've just been showing with experimental data, doubling the spray rate, the time, the pressure, is certainly not doubling the heat removal rate. And so we have to have a more fundamental understanding of heat transfer. And so again, we can kind of look at the effect of spray, and here we're looking at kind of the effect on directional acidification. Again, this is simulation where we're spraying the top of the casting, and we're looking at the effect of changing the spray time on the gate. And so as we, on the runner I should say, as we increase the spray time, then we can actually increase our pore fraction. What's happening is that we're cooling the gate too much at the surface. It's solidifying very, very quickly. Therefore, we're less able to feed shrinkage, and therefore we're actually increasing our pore fraction. We can look at it the other way around. What happens if we change the amount of spray on the top of the casting? So, for instance, if a nozzle is blocked at the top of the casting, we're spraying for 0 time, and so we're going to get more shrinkage porosity at the top of the die here. And so both of these are kind of opposite in terms of what we would like to do. As I said, what we'd really like to do is get directional acidification from the extremity to the gate. And so really what we want to do is have the gate hotter, have the extremity colder, and therefore we can get initial acidification at the extremity of flow back to the gate, and that gives us longer time to feed shrinkage, and therefore we can do a better job of pushing more liquid into the mold. And that's kind of shown here a little bit here in terms of looking at the in the extreme. If we just insulated the gate, i.e. we had no heat extraction at all from the gate, we do a better case where we can reduce the pore fraction. But even so, even with the insulated runner, we're not totally eliminating porosity. We're going to get porosity in some of these heavy areas. And then the final, I think this is the final slide here, in terms of metal holding temperature. Again, data from 1979 transactions paper. Lower holding temperature, we get increased density, lower porosity. Maybe it's because we're getting close to semi-solid casting, we're getting more viscous, partially solidified injection. And in fact, the is it the ATM process out of Australia was kind of looking at this in terms of reducing porosity. And then in terms of a higher holding temperature, we get a better surface finish. We're getting 100% liquid injection, so we're going to maybe increase our liquid contraction in terms of doing, getting more porosity.